Hello everyone, this is Professor Wilkerson again. This time we're going to talk about an introduction to the exercise 29 in contemporary activities by Hoff and Wilkerson, contemporary activities in astronomy. We're looking at exercise 29 where we're going to look at the distribution of star clusters on the sky. So we're going to look at the distribution of open star clusters and globular star clusters and ask what we can learn about those two objects, those two classes of objects, by looking at their distributions. And what might we learn about the galaxy? So we're making the transition to start thinking about big picture items in astronomy now. We're going to start thinking about clusters, the galaxy, and star clusters, the galaxy, the Milky Way galaxy we live in, and then the distribution of galaxies and the universe on a large scale. So that's where we're moving here in the next couple of weeks. So this is fun stuff. A couple of the ideas that we're going to work on, and we're just going to practice it here in this activity. So you'll see questions as you work through this activity. And what we want to do here is think about the concepts of homogeneous and isotropic. And so we're going to ask you, do these distributions look homogeneous to you? Do they look isotropic to you? And so the way to think about that is homogeneous means smoothly distributed. That's a simple way for us to think about it for the purposes of this class, is to say smoothly distributed, not clumped. Okay, so let's think about a forest. And I'm going to refer to a forest quite a bit as we talk about the distribution of stars and the distribution of galaxies. And think about you standing in a forest and looking at the trees, and what would you see? So if you stand in a forest and the trees are more or less smoothly distributed, so the number of trees per square meter is the same all around, then that's fairly homogeneous. If the trees are clumped, then you have a big clump of trees, some open space, a big clump of trees, some open space, a big clump of trees, some open space, a big clump of trees, and so on. So for these clumps of trees within your forest, that's a less homogeneous, a not homogeneous distribution. The distribution is clumped up on you there. Isotropic, for our purposes, we'll take isotropic to mean the same in all directions. So even if it's clumped, those trees are clumped. If you look this direction and this direction and this direction and this direction, and every direction you look, the clumping is the same. The distribution of clumps is the same. That's going to be an isotropic distribution. The trees are distributed the same in all directions. So isotropy is about the distribution in different directions, and homogeneity is about the smoothness of the distribution. So we're going to ask, are these distributions homogeneous? Do they appear homogeneous? Do they appear isotropic? Now recognize, one of the things we want to practice in this activity is recognizing that the appearance of homogeneity, or in particular the appearance of isotropy, can depend on where you are sitting. And we can't change where we're sitting in the galaxy, so we have to take that into account as we look at this. So for example, if you've got a forest, the forest probably looks isotropic to you. It might look isotropic to you if you're standing smack in the middle of a big forest. You see trees and the same amount of trees in all directions. But if you get out to the edge of the forest and you're standing out here on the edge of the forest, you see a lot more trees looking toward the middle of the forest than you do out toward the edge of the forest, toward the open field, for example. And so then it doesn't look isotropic to you anymore. It looks more trees in one direction than another direction, and that has nothing to do with the actual distribution of trees. It has to do with the trees within the forest. It has to do with the extent of the forest and where you are relative to the edges of the forest. And so we want to apply that kind of thinking to the galaxy as we move forward, and then to the universe a little bit more. So part of our trick here as young astronomers working on understanding what we can learn about the universe is to recognize that trying to understand and measure the universe while living deep down in the soup of the universe is a challenge. And we need to figure out what we can do, how that biases what we see, the fact that we're living down in this soup and trying to measure the soup at the same time. So this is a little bit of what we're working on in this lab. We're also trying to understand the structure of the galaxy and trying to understand how we can use the distributions of these clusters to recognize that they're probably not the same thing, open star clusters and globular star clusters. And we recognize that in other ways too, and we can recognize that from from work that you did in the previous exercise by looking at HR diagrams of the two objects suggests that they're probably not the same thing. We'll talk about this in class. But this is one way to think about looking at this. Just looking at the distributions. Are the distributions consistent with one another? Could these possibly be what we're calling globular clusters and what we're calling open star clusters? Could they possibly be different examples of the same thing, and actually so that we screwed up when we called them two different things, and we should have just called them one thing. And so we're gonna make a series of 3 graphs, and again, you can make the graphs in the graph paper that's provided for you in the book, or you can make the graph on other graph paper that you bring with you that you print off, and that's fine. So table 29.1 is the right ascension and declination for open star clusters. For those, we're going to make a graph of declination on the vertical axis versus right ascension on the horizontal axis. This is exactly the same axis setup that you've been using all term long for your on your constellation charts. So you're familiar with this type of graph. It's exactly what you've seen in the constellation charts that we've used in many different settings so far. Table 29.2 provides the same information for globular clusters. And you're going to make the same graph. Declination here, right ascension across the horizontal axis. Now, these are the clusters that appear. There are more clusters than this, and we have to cut the clusters somehow. We can't print this information for all of the clusters. We don't have time to do that in the laboratory here today. So what we're doing is we're choosing the clusters that appear in Charles Messier's list of objects. And Messier's list is about 110 objects that are interesting to us. They're fuzzy objects. Now, one of the fun facts of the history of astronomy is I think when Messier first made this list, he made the list to point out objects that really weren't interesting, to say, hey, here's a fuzzy object, but it's not a comet. He was interested in understanding comets and knowing comets that were coming and going and helping you to say, hey, you found a comet, but you didn't want to confuse one of these things for a comet. So don't pay attention to these things. Here's a list of 110 things that you might confuse for a comet. So be aware of these things. Be careful about these things. Now today, these are extraordinarily interesting things. Star clusters, as we have in the lab here, nebulae, galaxies, all kinds of stuff on these interesting lists, different kinds of nebulae, star birth regions, the regions where stars have lived their lives and moved on. And so really wonderful, interesting things. We're looking at the globular clusters on his list, and we're looking at the open clusters on his list. And you're making these 2 graphs that we talked about. In addition to that, I want you to make a histogram of the right ascension values of the globular star clusters. The lab instructions walk you through what a histogram is and how to make it. If you haven't made one before, as I told you in class last week, I make a histogram of the number of trick-or-treaters who come to the door each Halloween in 15-minute intervals. So I know that as a function of time, and I can make various histograms out of that. But anyway, or various other graphs too. But a histogram basically says if you have a whole bunch of numbers, count all of them. So you have a whole bunch of values of something. In our case, the right ascensions of globular clusters is what we're working on. And if you have a whole bunch of values of some quantity, you break those values into bins. And so we bin. Physicists and astronomers will talk about, use the word bin as a verb to say, let's bin the data. Let's break the data into even chunks, okay? And so you break these into even chunks. In this case, you've got hours of right ascension. Maybe you want to break it into 1 hour chunks of right ascension, or 2 hour chunks of right ascension, or 4 hour chunks of right ascension. That's probably going to be way too much. So probably 1 hour chunks of right ascension is good. And then you just count up. How many are between 0 and 1? How many are between 1 and 2? How many are between 2 and 3? And how many are between 3 and 4, etc. And go on. And so when you make your histogram, the number that fall between 0 and 1 is what you plot right here. Suppose 2 fell between there. Then you draw a line up here and across it 2 and down. And you've just made a histogram with a value, the number that are between 0 and 1 at 2 here. Suppose there were 4 that appeared between 1 and 2. Then you go up here 3 and 4. And you come up here, you walk up to 4 and come across and drop down to 2. Then suppose there was only 1 between 2 and 3. And so between 2 and 3, you come up 1 and over and down. And maybe there's none between 3 and 4, so you just go there at 0. And then maybe suddenly there, out of nowhere, there was 5 up here between 4 and 5. And so between 4 and 5, you go all the way up here to 5 and drop down, and you've made yourself a histogram. And you want to do that for all 24 hours of right ascension. One of the tricks, one of the pieces of artistry of doing any kind of analysis work in the physics lab or the astronomy lab is binning data and choosing the right size bin. If you over bin, if you make your bins too small, you don't have enough data in any one bin. You can't see what's going on. There's too much fluctuation, too much what people call noise. It's Poisson counting statistics is probably better, but what people call noise, there's too much noise in the data, and it jumps up and down from bin to bin, and all you're seeing is just this messy noise that's in there. If you underbin your data, all you get is all your data in 1 or 2 bins. You can't really see how the distribution, if the distribution has a peak. So one of the things you like to look for is to say, does this distribution have a peak? Yeah, it has a peak. It's right there. And so you've just measured the peak of where that is. And you could get a visual. Or one of the things I often look for when I bin data is it bimodal? Do I see a peak here and another peak out here? Just by taking a straight mean or median of the data, you're going to miss things like bimodality, and you have to be very careful about that and recognize that this is the kind of thing that's going on in your data sets. And so, or does it have a tail? You might have a peak and it's sharp on one side, but it's long on the other side. You have some kind of long decay over there. What's that telling you about the nature of the thing that you're binning, the nature of the thing that you're making histograms about? So this is a graphical analysis technique that is very interesting and powerful and useful, and we're going to practice it here today. So I'd like for you to make a histogram of the right ascensions of the globular clusters and use that histogram to talk about. Now, unlike what we did in exercise 28, where I want you to write me a summary of what you did and write well-developed paragraphs to talk about what you learned about the open star clusters in the galaxy as you went through that. In 29, no written summary at all for me. I just want you to answer all of the questions that pop up in the text. So as you're going through the procedure, there are procedure questions that are interwoven, interlaced in that procedure. Answer them as they come up. So write me the answers to those, and then also answer all 6 discussion questions at the back. So you've got 6 discussion questions back here. Answer every single one of those discussion questions and all of the procedure questions, and turn in your 3 graphs. Your graphs of right ascension versus declination versus right ascension for the open star clusters, declination versus right ascension for the globular star clusters, and your histogram of right ascension values for the globular clusters. And that's what we got. That's what we got for the week of November 2, are these 2 parts. And we'll see you all in lab this week. Take care, everybody.